nth order initial value problem. Has the form, the equation nth derivative of y with respect to x equals some function of x, y, and the n derivatives of y, along with a set of conditions. Y of x naught is equal to y naught, y prime of x1 is equal to y1, y prime of x naught is equal to y1, so on and so forth. The n minus first derivative of y evaluated at x naught is equal to y sub n minus 1, where each of these constants y naught, y1, y n minus 1 are the initial conditions. Now we'll shorthand an initial value problem. That should be up here. I, V, P. And we'll shorthand initial conditions. I, C. Now, solving this entails first finding the n parameter family of solutions, then using the initial conditions to determine the n constants in this family. So remember those constants from last time, C1, C2, C3, up to Cn. So what we're going to do is we're now going to take a look at an initial value problem. So what we're going to first do is verify that x equals C1 cosine of 4t plus C2 sine of 4t is a solution to the equation x double dot plus 16x equals 0. Once we've done that, we're going to use the initial conditions. X of pi over 2 is equal to -2, and x prime, or rather x dot, of pi over 2 is equal to 1 to find the C1 and C2. So remember to first verify this is a solution. We're going to find x dot and x double dot. So x dot, -4 C1 sine of 4t plus 4 C2 cosine of 4t. X double dot, -16 C1 cosine of 4t minus 16 C2 sine of 4t. Now I'll just plug these in. So x double dot, we get -16 C1 cosine of 4t minus 16 C2 sine of 4t plus 16 times x, C1 cosine of 4t plus C2 sine of 4t. So what does this equal? So we're going to get a -16 C1 cosine of 4t minus 16 C2 sine of 4t plus 16c1 cosine of 4t plus 16c2 sine of 4t. And of course, this whole thing is equal to 0. And so this is indeed a solution. Now, to find the C1 and C2, we make use of the initial conditions. So x evaluated at pi over 2. Well, x was 16c1 cosine of 4t. I'm sorry, c1 cosine of 4t plus c2 sine of 4t. So we're going to get c1 cosine of 4 times pi over 2 plus c2 times sine of 4 times pi over 2, which is c1 cosine of pi over 2 plus c2 sine of pi over 2. Now, cosine of pi over 2 is 0. So we're left with c2 times sine of pi over 2, which is 1. And this has to equal, according to the initial condition, negative 2. So c2 is negative 2. Next, we use the condition x dot of pi over 2. So x dot, remember, is up here. So we get negative 4c1 times sine of 4 times pi over 2 plus 4c2 times cosine of 4 times pi over 2. So we get negative 4c1 sine of pi over 2 plus 4c2 cosine of pi over 2. Now again, cosine of pi over 2 is 0. So this becomes negative 4c1 times sine of pi over 2, which is 1, has to equal 1. And so c1 is negative 1/4. So our particular solution, which I'll denote x sub p, is negative 1/4 cosine of 4t minus 2 times sine of 4t. And that is how you solve an initial value problem. Again, we'll study how to find the parameter family of solutions called the general solution throughout this course. Then all we have to do is apply the initial conditions to that general solution, and we have our constants for our particular solution. We have two fundamental questions concerning initial value problems. The first is, does a solution exist? The second is, if a solution does, is it unique? Well, within the confines of this course, we can be fairly confident that most differential equations will have solutions, and those solutions will probably be unique. Most of the problems that arise in applications, however, are not so idyllic. It is desirable to know in advance whether a solution exists and whether said solution is the only solution. The next theorem, called the existence theorem, will tell us how to determine this. And this theorem will be offered without proof. So we let R be a rectangular region. In the xy plane that is defined by AB cross CD. And this region is going to contain the point x naught, y naught. If f of xy and partial f partial y are continuous on this region R, then there will exist some interval, call it I, that is defined by x naught minus h to x naught plus h, where h is greater than 0, contained in the interval AB and a unique function y of x that is defined on our interval. That is a solution to the initial value problem dy dx equals f of x y, and y of x naught is equal to y naught. So again, to iterate, this backwards e is shorthand for there exists. So if we can show that the function f of xy and its partial derivative with respect to y are continuous on some rectangular region in the xy plane, then we know that the initial value problem given by dy dx equals f of xy, y of x naught is equal to y naught, will have a solution over some interval. That concludes our lesson on initial value problems. Hope you learned something, and we will see you in the next one.